reactants change to product and product change to reactant at the same time or at the same situation in the same conditions, that is a reversible reaction. A very good example of reversible reactions is nitrogen reacting with hydrogen to produce ammonia. Now, this is happening in the same container. That nitrogen reacts with hydrogen, produces ammonia. This is an exothermic reaction. In O levels, you're not supposed to memorize why this is exothermic, but we can calculate that pretty easily. What we do is we make the bond diagrams, the Louis diagrams for this, and then we try to figure out how many bonds are being made or broken. So for example, over here, one nitrogen triple bond is being broken, 3 hydrogen bonds are being broken, and for every molecule of ammonia, there are 3 bonds between nitrogen and hydrogen. So in total, there are 6 bonds between nitrogen and hydrogen. So those are being made. So delta H comes out to be energy of bonds broken as positive and energy of bonds made as negative. And you just calculate it to find whether it's rising or whether it's falling. So in the case of this ammonia being made, I know that this is exothermic, which means they start at a certain level, go up, go down, and then the final level is lower than the first level. This is reactant, this is product, and this is how it proceeds. The system rises to a certain level. This is where it starts to go down. Now here's the thing. I will call reactant changing to product forward reaction, which means nitrogen and hydrogen reacting to produce ammonia. That is forward reaction. And in the forward reaction, this is my delta H. And this is my delta H, and that is my activation energy. Okay, that is the energy I have to give to the reactant so that they start to react. And delta H is the difference from the starting point and the ending point. Remember that arrows have to be clear. They have to start at the reactant, both of them, and they have to end at product for delta H and highest point for activation energy. Now for the backward reaction, this same thing holds, except for the backward reaction, this product is the reactant and reactant is the product. They have switched their sides. So now this is going to be activation energy and this is going to be delta H. And you can see that delta H is positive if you're going in the backward direction in this case, and negative if you're going forward direction in this case, because it is falling, so that gives it a negative sign, and if it is rising, it gives it the positive sign. Activation energy in both cases is going up, except for the backward reaction, activation energy is really high. So we say that that reaction has a higher activation energy than the other one. Remember that activation energy is basically the energy required to break the bonds. So in the forward reaction, you're breaking the bonds of nitrogen and hydrogen. In the backward reaction, you're breaking the bonds of ammonia. So breaking the bonds of ammonia in this case requires more energy than breaking the bonds of nitrogen and hydrogen, which is why the reaction goes like this. Sir, could you elaborate on your question? I couldn't quite understand this. Activation energy is always from the starting point to the top, the highest point, the complex state. All right. Now, how do reversible reactions happen in nature? They usually happen that initially any reaction starts in one direction. For example, if I have nitrogen and it's reacting with hydrogen, so initially nitrogen will react with hydrogen, it will collide. Remember we talked about collision. So nitrogen molecules will collide with hydrogen with sufficient activation energy, and they will start creating ammonia. But after a while, there will be many ammonia molecules in the container. And that means that they will also start to collide with each other. Initially, there is no ammonia, so no collision of ammonia. Nitrogen collides with hydrogen. and it keeps on going in that direction. But after a while, ammonia molecules are there and they are starting to collide with each other and break down and make nitrogen hydrogen again. And that is when the reaction starts to become backward. Now, initially, forward reaction is happening at a faster rate because there is more nitrogen, more hydrogen, and very little amount of ammonia. But after a while, ammonia is being produced, it's going to react and it's going to go back, which means the speed of reaction will have a mismatch. But then comes a time when the amount of ammonia being made, the forward reaction, is happening at the same speed as the backward reaction, which is ammonia breaking down to make nitrogen. And that stage is called equilibrium. To be specific, that is called dynamic equilibrium. Dynamic equilibrium is when the forward reaction is happening at the same state or same rate as the backward reaction. So it's not to say that only two of ammonia is being made and four of the reactants are being made. I'm saying that the speed at which ammonia is made is the same speed at which ammonia decomposes to make nitrogen and hydrogen. So what happens? The overall amount of reactants and products does not change. They don't have to be equal, but it does not change. For example, if this reaction, forward reaction produced this much ammonia, and backward reaction reduced nitrogen by this much, then the point when equilibrium has been reached is basically this one, where both the graphs are flat. And this does not mean that reaction is not happening. It simply means that no more ammonia is being made because the more ammonia is made, the more it goes backward. And more nitrogen is made, the more it starts reacting to create ammonia. So they keep on reacting, but they do not create a change that is measurable through concentration and all that. The reaction still happens. So that is reversible reactions. There's so many reversible reactions, like decomposition is one. For example, PCl5 can break down and produce PCl3 and chlorine. Now, of course, chlorine can react with PCl3 and produce PCl5. Okay. And when they do that at the same rate, we say they have reached dynamic equilibrium. So if you were to define dynamic equilibrium, what will you say? It is the state when rate of forward reaction is the same as rate for backward reaction. Remember that it is about the rate. It is not about the amount. It's about the rate at which it happens. Okay. Now this equilibrium can be disturbed, and that is the main point of reversible reactions. We call that Le Chatelier principle. Let me just show you what that is. This is Le Chatelier principle. It says if a change in conditions is made to a closed system. So closed system simply means that you are talking about that container where the reaction is happening, which is already in equilibrium. The system responds to counteract the change. It's really simple. The system opposes the change. Whatever change you want to make, the system will oppose it. Okay. And how will that happen? If your change made the reaction go forward, it will try to make it go backward. Okay. So that's Le Chatelier principle. I'm going to refer to this as LCP. In simple words, LCP says that the reaction goes opposite to the change that you have made. So what changes can we make? We can change the concentration. So if we change the concentration of, let's say, in this example, I change the concentration of chlorine, then the reaction will try to counteract that change, which means if I reduce chlorine, it will try to produce chlorine. If I produce chlorine, it will try to reduce chlorine. It's going to go in the forward direction if I decrease the amount of chlorine, and it's going to go in the backward direction if I increase the amount of chlorine. Similarly, I can change the temperature. Now let's suppose this reaction was exothermic and the heat was being produced. So if I did this reaction when the temperature was already high, then the reaction will try to reduce that. It will go in the backward direction because if forward is exothermic, the backward would be endothermic. It will try to reduce the temperature by going in the backward direction. Similarly, if it is already endothermic and I increase the temperature, decrease the temperature, it will try to increase the amount of kinetic energy over there, and it will try to go in the backward direction to counteract that. So all of these are basically based on Le Chatelier principle, which says that whatever you do, the system will try to counteract, system will try to oppose that change. So let's say we have a simple reaction in which we have three things reacting and producing something. So A is reacting with B, 2B, producing 3C. Okay. So if I increase C, the reaction is going to try to decrease it and go backwards. So if this increases, that means the forward reaction has increased. So the reaction is trying to or going to reduce the amount of C, use it and go back. So backward will speed up. Similarly, if I decrease the amount of B, so I've reduced B, so system will try to produce B. So we'll hit back. If the concentration of a reactant increases, the reaction goes forward, for example, in this one. Why? Because you have increased the amount of reactants. So they're going to collide more, they're going to react more, the reaction is going to go forward. And that means equilibrium will move to the right. So we say it's moving to the right because it's creating more products. So the concentration, when you increase it, you're basically adding more something. So that extra that you added is going to react. Similarly, if you increase the concentration of a product, like for example, in this reaction, I added water, then what will happen? That water, the extra that you added, is going to react with this substance, and it's going to go backwards or going to the left. So we say equilibrium shifts to the left, or equilibrium moves to the left, so that it produces this. So whatever you increase, the system will try to decrease it, and that is how it affects the equilibrium, affects uh, concentration of a reactant. Similarly, it can also be affected by pressure. But for pressure, you have to remember that pressure only affects gases because gases are free to move. So when you apply pressure on them, they start to collide more, because remember, gas pressure is because of collision of particles with the container. So as we have gas, the particles are free to move, they will collide with each other. And if you try to change the equilibrium, let's suppose you apply more pressure. So the side with more gaseous moles, that will create more collisions. And when they collide more, they're going to react more. And so the reaction goes into the opposite side. So the side that has more gaseous moles will have greater contribution to the pressure. So whenever pressure is changed, number one, it will only affect the gas. Okay. So first thing, pressure will only affect gases. Now, if you have more moles of gases, then they are going to be affected more. So let's suppose I increase the pressure. So the side with more moles is going to react more and go to the other side. So for example, in this equation, you have 2 moles on the left side and 4 moles on the right side. You see, it doesn't matter what gas it is. As long as there's more moles, there will be a reaction. So what happens is that as more moles on the right side and 2 moles on the left side, so the 4 will react and go to the left side. So if I increase the pressure, it's going to go towards the side that has less gases, so that it decreases the pressure. Similarly, if I decrease the pressure, it's going to go towards the side that has more moles of gases, so that it increases the pressure. So all that the reaction is trying to do is counteract whatever change I do. Okay, so that is effect of pressure on the equilibrium. But LCP is still there. LCP says that as you increase something, the system tries to decrease it. So system is always going backwards compared to whatever you're doing. Now, the third factor that affects it is temperature. And temperature is pretty simple. If you increase the temperature, you're giving them more energy, which means it will try to absorb that energy and go into the endothermic side, whatever that is. Where if it's forward, it will go forward. If it is backward, it will go backwards. But the key point is that you are giving it more energy by increasing the temperature, it will try to absorb that energy. Similarly, if you decrease the temperature, then you are already taking energy away from the system. So it will try to increase the temperature. It will try to give more energy out. So how does it release more energy? Exothermic reaction. So it will try to go towards the side that has exothermic reaction, whatever that is. And we'll say that equilibrium has shifts to that side. These things in the bracket, they're just in case you're interested. You don't need to specify which direction energy changes are going. So temperature is easy. You give them more kinetic energy, so they absorb it. And if you take energy away from them, they try to release it. So in either way, it's going to go towards the side that is opposite to what you did. You increase the temperature, it's going to decrease it by going to endothermic. You decrease the temperature, it's going to increase it by going into the exothermic side. So that is the effect of temperature on equilibrium. But that's not all. Temperature also has another effect on the rate of reaction. You see, when the particles have more kinetic energy, they collide more, which means the rate of reaction is also more. So not only are they changing the equilibrium and going to one or the other direction, they're also doing it at a faster rate. Okay. Yes, Seher, when we have pressure changes, we only consider gas moles. And solids and liquid do not count over there. We don't consider them. That's a very important point. All right, so for temperature, all that matters is that which side is endothermic or exothermic, depending on what change you made to it. Now, let's suppose we have this reaction, the one that I just gave you the example of. Now, this is endothermic reaction. So let's suppose I'm having this reaction at 200 degrees Celsius and there's equilibrium. If I raise the temperature from 200 to 400 degrees Celsius, what will happen? Will the forward reaction be increased or will the backward reaction be increased? Like the rate. So for that, we have to understand that this is an exothermic reaction. And what have we done? We have increased the kinetic energy. Now, because we have increased the kinetic energy, we have given them more energy. So the reaction is going to try to release that energy. Okay, reduce that energy. And because I have increased the temperature, it's going to try to decrease the temperature. So it will go into the forward side. Because forward side is endothermic. It absorbs the energy. Exothermic releases energy and endothermic absorbs energy. So मैंने kinetic energy ज़्यादा दी है, वो उसको absorb करने की कोशिश करेगा, endo में चला जाएगा. Now forward reaction will increase and we'll say that the yield has increased for the forward reaction. Now, obviously, the rate of the backward reaction will obviously reduce in that. But all of this is happening when you have given them more kinetic energy. So they collide more and the rate is also more. Equilibrium shifts to the right side, but rate is also much faster. So that is an important point to remember, that even in exothermic reactions, when increasing the temperature will mean that the reaction is going backwards, like the equilibrium goes backwards in an exothermic reaction if you increase the temperature. But even then, we increase the temperature. Why? Because the idea is to compromise on how much of the product is made and save time. If you have an exothermic reaction, for example, nitrogen reacting with ammonia, nitrogen reacting to produce ammonia, if you have a reaction like that, it is exothermic. And we would expect that, okay, because it's exothermic, we would like to produce more ammonia. So let's just do it at low temperature, because that way the system will try to increase the kinetic energy, increase the heat, and obviously it will go to the right. But the problem with that is that at low temperatures, the reaction happens too slow, even if they're producing ammonia. Equilibrium is towards the right. Sorry. But the reaction is happening too slow. And so we save time by having this reaction occur at very high temperature. Okay. And that is because we want to save time. In short, low temperature favors exothermic and high temperature favors endothermic, if you want to note it down somewhere. Low temperature favors exothermic and high temperature favors endothermic. But the idea of compromise is to have high temperature for exothermic, to compromise in yield, but save time, have a faster rate. So here is a reaction. So C2H4 is ethene, and let's suppose ethene is being reacted with steam to produce ethanol. All of these are gases at this temperature. Okay. So what happens? Let's suppose this reaction is happening at 300 degrees Celsius. So this is gas, and this is gas. It is balanced. And right now the temperature is 300 degrees Celsius. If I change that to 500 degrees Celsius, what will happen? So the options are forward reaction will increase, backward reaction will increase in speed, or nothing will happen, or we need more information. Which of these answers would you choose? The question says the temperature is changed from 300 to 500. Will the equilibrium favor the forward side? Will it favor the backward side? Will it not change, or do you need more information? Since we do not know whether it's endothermic or exothermic, we cannot say which side the equilibrium favors. Good, very good. Now let's say this reaction was happening at 5 atmospheric pressure, and now the pressure has changed to 100 atmospheric pressure. What will happen? Will the reaction favor the forward side, the backward side? Will it remain unchanged? Or do you need more information? Now remember that pressure only affects the gases. We have gases here, but the number of moles are different. On the left side, we have 2 moles. On the right side, we have 1 mole. So if we increase the pressure, the reaction is going to go forward to reduce the temperature by going towards the side with less moles. So excellent, Zainab. Yes, it goes forward. The equilibrium favors the forward side. This substance, phosphoric acid, is added to the reaction mixture. What will happen to the equilibrium? Will it go forward, backward, remain unchanged, or do you need more information? Why? Why will it remain unchanged, Zainab? You see, catalyst, yes, you can unmute. Feel free to unmute yourself and answer the questions. Typing will take away so much time.
I'm not sure, but I think because catalysts affect the rate of any reaction and not whether it's like endothermic or exothermic, not the overall energy of it.
Excellent. Basically, catalysts just give us an alternative pathway for a reaction, and that pathway reduces the activation energy. So you see, let's suppose this was an exothermic reaction. Let's suppose it was. The question does not tell us. Let's suppose this was the case. But if I add a catalyst, it's going to reduce this activation energy. Now, earlier on, the activation energy was like this for forward reaction and this for backward reaction. But now you can see that with this new change, the activation energy for forward is less, but also the activation energy of the backward is also less. So catalyst simply speeds the rate, and it does it for both sides. Catalyst does not differentiate between them. So the rate is increased. The reaction happens at a faster rate, but equilibrium will remain unchanged. The rate of forward is still the rate is backwards. It's just that both rates are higher now. It will not affect the yield as well because the rates are still the same. Next change is that we add more steam. How will this affect the equilibrium? Will it move forward? Will it move backward? Will it remain unchanged? Or do we need more information? According to LCP, we know that anything, if you increase its concentration, the reaction tries to reduce its concentration. So if you have increased the amount of steam in there, then the reaction is going to use up the extra that you have added, and it's going to make more ethanol. So the reaction moves, the equilibrium moves forward. Excellent. So all of this is basically helping us understand how something will affect the equilibrium. Okay, so to summarize it, here is what we know. And that is the whole forward and backward reactions. There are two reactions in our syllabus for reversible reactions for which you need to memorize the requirements. So the first one is called Haber process or Haber process. Haber process is when you take nitrogen, you react it with hydrogen in a reversible reaction, producing ammonia. It's an exothermic reaction. All that I'm saying, you need to memorize it, okay? Temperature is 450 degrees Celsius. Now there is some range acceptable. You can say 400, you can say 500, but you won't say 200. And although in some mark schemes, even 200 is acceptable, but 450 is a good choice. Similarly, for pressure, pressure is 200 atmospheric pressure, or you can say 250, or you can say 220, anywhere around it. Similarly, uh, catalyst is iron. So you need to provide iron catalyst for this reaction to occur. Uh, Also important things, what is the source of nitrogen? So source of nitrogen is fractional distillation of air. And source of hydrogen, again, you need to remember this. Source of hydrogen is cracking iron. Similarly, tests for ammonia, the test it turns damp red litmus blue. And ammonia also reacts with acids or to produce ammonium ion, which gives ammonia with NaOH. So if you add NaOH to it, it reacts as an acid, releases ammonia. Similarly, ammonia is also released when you have nitrate ion. Take the nitrate ion, you add NaOH, aluminum foil, and you heat it a little bit, and ammonia is released. So you see, three main facts you need to memorize, three main tests for ammonia in your syllabus. I will be sharing a fact sheet with you. You will need to memorize all of it, and I will take oral tests from you later on in the month. Okay. The second reaction that is important from this point of view is that of this is called contact process, where sulfur dioxide reacts with oxygen to produce sulfur trioxide. Now, this is an exothermic and endothermic. Sorry, this is a reversible reaction. The conditions are the temperature is anywhere from 250 to 450 is fine. So just say 450, and pressure is 1 or 2 atm. It's low pressure, and the catalyst is V2O5. Now, for this one, what's important is that you must know the test for sulfur dioxide, sulfite, and sulfate. Sulfur dioxide is basically a reducing agent since it makes sulfur trioxide. So sulfur dioxide reacts with KMnO4, which is oxidizing agent, and makes sulfur trioxide. Okay, goes makes it go purple to colorless. Sulfite ion reacts with barium. Now remember, whenever you have barium nitrate or barium ion, that is a test for sulfur ions. So barium ion tests sulfur ions. So sulfite, you add barium nitrate, produces white precipitate. Sulfate, you add barium nitrate, produces white precipitate. But if you add HCl, sulfite will dissolve, sulfate will not. Okay. So these tests are also important. Similarly, another fact you need to memorize is that sulfur dioxide is used to bleach wood pulp for paper industry. Sulfur dioxide is used for food preservation, and sulfur trioxide is used to make sulfuric acid, which is then used to make paints, detergents, and God knows what else. Similarly, ammonium is produced or nitrate is used to make fertilizers. Again, because this is only a diagnostic session, we are more really concerned with the overall concepts and not these pieces of information. I can share these with you and you can memorize them. I would expect you to do that.